So today is the second day of our lecture cum tutorial, where we are trying to discuss about the two tools, packages that mainly the people in high energy physics, they use to analyze the data. And the plan for today will be to quickly visit exercises 2, 3, 4 of day one, but obviously not going through line by line, each giving details of each line, but just an overview. And then we will start with one or two simple examples of uproot. And then we will move to the advanced use case of PyROOT and uproot. So we will see how much we can cover today, but then obviously tomorrow there will be another session when we are again going to look at the advanced use cases of PyROOT and uproot, mainly for the machine learning applications. So just to recap, we have PyROOT, which basically creates the proxies to the C++ objects that we have in root. All the functionalities that we have in root, we can access them by PyROOT, and we can convert the data from the root data type to, let's say, Python data type. Like we can make NumPy arrays and etc., which are Python data types or Python objects from, let's say, C++ vector, which we have seen yesterday. So I will today start with a brief description of uproot, and then we will move. Oh, no, maybe before going to that, I will probably, as we are recapping the PyROOT framework, so maybe it's better that I go and show you the exercise 2, 3, 4 quickly, and then come back to uproot. So let me unshare and share my terminal again. So hopefully some of you or most of you have gone through the framework and also could install root and uproot. If not, obviously you will still try to do that, and let me know if you have any problem. I know some of you wrote to me, and I know there are some problems, but this is normal, and you have to, I mean, I didn't have enough time to answer you quickly, but still, hopefully now most of the problems that you were facing are fixed. If not, we again revisit them and try to understand. So let me share my screen again. I hope you can see my screen. So I'm still in day one directory. You can see. So this is the GitHub repository that we have created, cloned, and there are multiple subdirectories inside the repository, day 1, 2, 3. So we will look at day one, some of the exercises in day one, and then we will move to uproot. Jupyter notebook. That's how you, okay, I'm not in the right environment. So this is what is going to happen if you are in the wrong environment. So I'm going to activate the right environment where my root is installed, and obviously also Jupyter. Okay. Now it works. Fine. So as I said, I will quickly go through the second, third, and fourth example. Hopefully you remember that we have created yesterday one root file. I have shown, and you already have seen what we have stored inside this root file. Actually, it was a tree, which is called the class is called TTree, and the name of the tree that we created is tree with a small t. And then using PyROot, or all of these are features of root. Basically, everything is written in C++, as we already have seen. So you can get the tree, which is a proxy to the C++ class TTree, and then you can do almost all the things that you can do with the C++ class. So this TTree has a method called print, or function called print, this TTree class. And you can also do the same in PyROot. You can then check what are the branches which are saved in your tree. And then you can also see how many baskets. So baskets are the places where this data is stored. So there are, these 1,000 entries, 1,000 events that we have stored inside this tree are obviously not stored in the same basket, but they are saved in chunks of baskets, which is done for optimization of memory, but whatever. So that is not important for today's discussion. So, and then this is how we create a root histogram. So as you remember that we import root as RT, and then if we say rt.th1f, this is going to create a histogram where it has, this is a constructor of the th1f class in C++, but then it has the same kind of syntax. The PyROot tried to keep the same syntax as we use in C++, so that whoever have used C++ root can do the same in PyROot without learning something new. Basically, that was the idea. So the first thing is that the name of the root, the histogram, then the title of the histogram, then the number of pins of this histogram that you want to create, and then the range, which goes from 0 to 10. Obviously, we can change if we want to change the range of the histogram, but okay, in this case, let's say we are trying to create the PT distribution. So as we know that we have the PX and PY in the tree. So what to loop over all the events, this is Python, and that's why it's so easy to write. As you can see, if you write a C++ code, it will be much more clumsier. It will look a bit complex, like when you write for loops, and then you have to, if you remember that you have to set the data type for each of the variables that you are defining, either int or float, and etc., which is already, like in Python, which you already learned that in Python it is inferred. So basically, whatever variable that you create or you get, Python tries to infer the data type from the right-hand side, like px equal to event.px. Basically, this px gets the data type from the right-hand side. It tries to understand what kind of data it is, and then Python in the backend tries to assign that data type to px. But whatever. So this is very simple, and that's why we use Python, right? So it is easy to write and also easy to understand. So we loop over all the events of the tree just by for event in tree, which I hope you know already. You have gone through the Python course, and then you get the elements of each event by, as you can see, just by calling px, but this px is actually a variable or a branch inside this tree. So as you can see, So event by event, you are accessing the PX branch. So if you remember yesterday, when we were looking at the tree, we saw how did we fill the tree? I can quickly go back to that just to tell you. So what we have filled, we filled random Gaussian numbers. So a random number which follows the normal distribution, right? So that's how we fill the PX, PY, PZ, and energy. So, and obviously with variable lengths for each event. Not each event has the same amount of, you can say, particles. So for the first event, it has only one particle. Second event has 2 particles. Third event has 3 particles. So it was done like that. And obviously, as you can see, the last event, which is the 1000th event, has 1000 particles in the collision, which is obviously we are trying to make a dummy file. So this doesn't make any sense, but still we are trying to use that. So it accesses all these PX and PY from the tree for that particular event in that event loop. And then we are trying to construct a PT variable, which, as you can see, it's a Python list, right? So PT is equal to a list, an empty list in Python. And then what we are doing, we are looping over PX, because as we have seen that in each event, this PX is a vector, which means it has some number of entries. So what we are doing is we go inside the event, we do a for loop on the event, we go inside the event, and then in that event, PX is a vector. So we again loop over all the PXs. And then what we are doing, we are trying to construct PT. As you know, this is the transverse momentum, so which should be the square root of PX squared plus PY squared, kind of. So yeah, so that is what is being calculated, and then PT is being filled. And after that, what is done is PT is a list. So you can call sorted, which is a function in Python, which basically sorts the list that you pass as an argument. Here we are passing PT. And what we want to do is that it sorts the PT list in the descending order. That means the first element should be the highest PT value for each event. Now, and then what we are doing, this is how we fill in root and also obviously in PyROOT. So we do histogram.fill, and that's how we fill a histogram. And we are filling the first element of this sorted PT list. So basically what we are trying to do here is to fill the leading PT, the PT of the leading PT particle or highest PT particle. And then if we want to display that, again, there is a class in root, which is called tCanvas, so which creates a canvas. And as you can see, canvas also has some number of arguments. Again, the name of the canvas, the title of the canvas, and the number of pixels that you want to have for this canvas. And then there, after you define the canvas, you can draw the histogram on the canvas. And then you have to, in Jupyter Notebook, you can do canvas.draw, which will draw the canvas, as you can see here, with the histogram that you have created, right? And obviously, you can also save the histogram by saving the canvas. So as you can see, for that, this is also save as is one of the methods of this tCanvas class, right? And this takes one argument, which is the name of the output file. So where you can say what should be the name of the output file, it's user defined. And at the end, you can obviously close the file if you want. And I'm not going to go through all of these. So basically, these are some ways to decorate your plot. So as you can see, before you didn't have any title on the x-axis or the y-axis, or there are many things that could be improved. Like now, as you can see, I have a title on the x-axis, which is called PT in GV, title on the y-axis, which is event. And I have also added some text inside the plot. And you can also have some legend. So all these things can be done using PyROOT, which basically is accessing root in the backend. Now, again, there are more modifications. If you obviously, you should go through this exercise to understand everything in detail. But basically, this is what can be done using PyROOT. So you have a root file, you read it, you access some branch, and you get the data from the branch, and you make a plot of that. So this is very easy in root or PyROOT. And as you can see, I mean, you are interchanging between Python and C++ because you are actually accessing a C++ objects as a vector, PX vector, but then you are storing them, calculating transverse momentum and storing that transverse momentum in a Python list. So that means you are playing with both C++ and Python, but you do not understand that because everything here in front of you, the code is written in Python. So to you, everything is Python. But actually, as I said, we are running C++ in the backend. Again, there is another way, another thing which is used often in high energy physics. That means not only plotting one variable, but you can also plot two variables. As you can see that here I have created another root file. I mean, you have to create another root file to do this. So you create another root file, which is called PyROOT exercise 1_2 by changing the random number, let's say the Gaussian, which you took 0,1, which means mean 0, standard deviation 1. You can change it to something else and reproduce another root file. And then what you can do is you can make two histograms, one for each of those files, and then fill them, obviously, by looping over each of those trees, which you saved inside each of the files. And then again, the same thing that we would like to do is to plot, but this time we want to plot them together on top of each other. I mean, there are ways to do that. I mean, obviously, I'm not going through each line, but this is how you do it. And then you can also make a stack plot. Sometimes this is very useful because suppose if you know that when you do the collisions, all kinds of processes can happen. Basically, that means you can have, let's say, for example, if you do some collisions, there will be some QCD process. That means some number of jets will come out without any interesting thing. And also in some cases, you will see there will be some Higgs which are produced. So what you can do is you can, for all the events that you collect, you know that among them, some of them are QCD, some of them are Higgs. So you have to stack one on top of other to get the total distribution. For example, for PT, you have some process which is sample 1, some process sample 2, and what you will get is the sum of these two. And this sum is done bin by bin. So basically, this is something useful. Hopefully, if you already use root, you know, and if you are going to use it in future, you will also learn. Then I'm going to the exercise 4, where, as you can see, it's a bit more another step towards calculating some more complex variable. As you can see, I create particle 1, particle 2, which are T-Lorentz vectors. Again, so in root, you have a class called Lorentz vector. So you can already create this T-Lorentz vector class, which has some functionalities. Like, first of all, you can assign the px, py, pz, and energy of each of those particles, as I did here. And then once you have the two Lorentz vectors, to get the invariant mass, you just sum the two Lorentz vectors, and then T Lorentz vector has a method called M, which actually returns the mass of that Lorentz vector. So basically, this will give you the invariant mass. I was discussing yesterday that suppose you have two photons coming out from the decay of Higgs, and then you have two photons, you have to reconstruct their Lorentz vectors by using all the measurements that you have done using the detector. So you have to have the Lorentz vectors of these photons, and then you calculate the invariant mass of these two photons. And this is how you can do that. And then you fill the histogram, and then obviously you try to plot it as we did before. But obviously this doesn't make any sense. But still it has, I mean, this is the procedure that I'm trying to show. And not only that, you can also try to fit the histogram that you have created by using some functions which are already defined inside root, which is another facility that you have if you use root or PyROOT. So as you can see, I am defining a TF1, so one-dimensional function, which is another class in root. And what kind of function I'm trying to create here? It's a Gaussian, because hopefully, let's say I know that it will be a Gaussian. So it's a Gaussian, and yeah, so this is the range from 0 to 100. And then what you do is just like, it's so easy to do here. As you can see, you just call histogram.fit, and then you pass this TF1 object that you have created, right? And then basically that will fit the histogram, and not only fit the histogram, but also obviously you get the parameters of the fit after the fit is done. Basically, best fit values of mean and sigma of this Gaussian. And then you basically plot this. You can also plot the TF1 on the canvas, as I did, right? So here, so you can see not only you can see the histogram and also the fitted function. And in the next step, I'm just going to show the fitted values, best fit values of these parameters. So like mean is 19.22, which is close to 20, as you can see from the histogram also. And the standard deviation is 2.9, so which is something. So these are not concrete examples. Obviously, these are not taken. I'm going to show you such example of where I will analyze real data, which was taken from the Atlas detector. So we are going to look at that, but this is just a small example of to show you what we can do using PyROOT, basically. Now, let's come back to the slides where I would like to show you the examples of uproot. Okay, so before going to that, may I ask you if you have any question from the exam exercises, if you have tried them, or if you didn't try while we were looking into those exercises. If you have any question, you can obviously raise your hands, or you can already speak.
Sir,
Hello, sir.
Yeah, please go ahead.
Okay. Yes, please. Obik?
I couldn't run
Okay.
the exercise 3 actually for some reason.
Sorry?
Exercise 1 and 2 I could run. Hello?
Yes. Yes.
I could run exercise 1 and 2 but properly, but exercise 3 I couldn't run properly. It is
What do
showing
you
some
mean by
error.
couldn't run? Does it mean that you got some errors?
Some error, yeah.
Okay. Obviously, we can talk about it, but I think that will be a bit of that will take some time from our. Already, we have limited amount of time, so I probably will not be able to fix the problem that each of you have. Maybe those kind of problems can be separately solved by sending me an email and discussing outside this these lectures. Okay. if you can follow what I was saying, that's fine for the moment. But obviously, I would like you to run all these exercises yourself after the lectures, let's say, and then come back to me by email that, okay, I ran it and this is the error that I got and how to solve that. Okay, maybe that will be better. Otherwise, we will lose a lot of time to discuss and debug the problems. And obviously, I'm sorry for that because we do not have enough time to discuss all the problems that all of you have. So that's why, yeah, let's do it offline. Ovik, you had some questions.
Yes, sir. Sir, when we do our analysis with C program and we read a root file, so normally we create a lot of pointers to avoid like creating a buffer. So like is PyROOT doing something like that in the backend?
Yes, yes. So there are a lot of optimizations which are actually is there. And PyROOT is with that. That is why it is fast, much faster. Okay, okay, I forgot to show you another thing. Yeah, thank you for asking this question. And also you asked a question yesterday. So I wanted to show you something about that. So which should be inside day 2. By the way, so I have updated the GitHub repository. So if you, okay. So let me turn it off. Okay. With new exercises, as we discussed yesterday, that we are going to update each directory every day. So I have already updated that. Okay, so just to come back to the point that Ovik raised yesterday, and also he's asking such questions today also. So that what about the performance that we could achieve using C++, like using pointers and references, you know, I mean, which are not directly creating an object, but actually you are, whenever you are trying to access some object, you use pointers or references, which are light, and you do not need to, you know, copy the object multiple times, which will obviously at some point blow up your memory, the memory use. So sometimes, which is not what we want. So, oh, I probably have stopped sharing my screen. Okay, let me start again. So here is an example that I would like to show you how PyROOT can be much faster than normal Python. So again, we are importing root, but in this case, as you can see, on top of root, I'm also importing side by side the NumPy. And then what we are trying to do here, so here, so as I already told you that there is a interpreter in root. Its root is something like Python. So as you know that generally for C++, I already discussed, generally in C++, we have to compile the code before we run it, right? But in root, even though it is C++, it's written in C++, but still it has the feature using clean that you can, like Python interpreter, you can interpret one code line by line inside root terminal. Hopefully you remember we did it yesterday, or we tried to, yeah, as you can see, we tried to load one file and then we come to the command prompt, like the interpreter of root. So root 0, root 1, these are the different lines of command that we are running. .ls is one of the C++ command that we are running here inside the interpreter. Tree.arrow print, it's a C++ command or C++ code, which we are running inside the interpreter, and it's doing that line by line. So which is something similar to Python, right? So we can do this in Python. So we can do Python 3 or Python, and then it returns the interpreter, and we inside there, we can run one line by line each of the code that we have, and it will run it like that. So the same thing is possible with root also. But okay, so what I was trying to show is we use this feature of root, the interpreter, and then we can pass, as you can see, a chunk of code, which basically is passed as a string, as you can see here. So what it does, so what we are trying to do here is we have two variables, v1 and v2, and they have a particular size, which we, as a user, we are going to define what should be the size of that variable. But at the end, what we want to return as a C++ class, C++ function, we want to return the largest sum of all possible combinations of v1, elements of v1 and elements of v2. So v1 has some number of elements, v2 has the same number of elements. They have the same number of elements. That is the size. And then we want to check for each element of v1, we want to sum with each element of v2, and then check which sum is the largest. And that is what we want to return here. And as you can see, for that, we wrote this set of lines, so which loops over v1 and loops over v2. And then what we are trying to do here is we are creating a temporary variable, which basically every time it sums over the two elements of these two vectors. And then if this temp is greater than the previous sum, then you update the value of r. That means you store, if it is greater, then you store r. This is how you find the maximum of, let's say, an array. But here we have two arrays and we are summing them and then trying to find the maximum of all the sums which are possible. And at the end, you return the maximum, right? And as you can see, this is clearly a C++ code, as you can see. But then what we are trying to do here is using PyROOT. We would like to compile this, not compile, but we would like to use this function, C++ function, which is the largest sum. But another interesting part is that now we are not creating standard library vector here. What we are creating is basically NumPy vector or NumPy array, sorry. NumPy array, but this NumPy array is of size 100. Let's say we want to create 100 elements for each vector. And then we want them to be floats, because in this function, we declared these vectors to be floats. So what we are doing here, again, is we are creating two NumPy arrays, which are uniform random NumPy arrays. So that is why it is random. So NumPy package has this random method by which you can create random numbers. And in this case, it is uniform random number. And you create two vectors, or in this case, NumPy arrays, sorry. And then what you can do is you can run the largest sum function that you have created using C++. But then you pass these NumPy arrays, v1 and v2, as you can see, with the size, of course, which are the arguments of this largest sum. And as you can see, PyROOT is translating these NumPy arrays into standard vector, and then passing them to this code and returning us the largest sum, right? So, and as you can see, this whole calculation is done on an average in 40 microseconds. Whereas if you do the same by, let's say, writing a Python function, we can do the same in Python. So you define a function which is largest sum, As you can see, this is how you define a Python function, obviously. And this is how you define a C++ function, which is much more complex, but it's doing the same thing than this Python function. They both do the same thing, but writing a Python function is very easy, as you can see. So you loop over x1, x2, which are the two vectors. And then again, you do the same thing, that you return the maximum of the sum. And obviously, this is how you try to find the maxima. And then if you run this function on V1 and V2, you see it's taking about 700 microseconds. So as you can already see, it's about, let's say, not 20 times, but somewhere close to 20 times, 15 times, let's say. So, and here we only have how many? 100. The size of these vectors are 100, but think about petabytes of data, like millions, billions of events. If you scale that, you will see that it's unmanageable using Python. Obviously, you can't do that. But this is the answer to the question that Ovik just asked, that this is why Python actually, sorry, not Python, PyROOT actually does all this kind of optimization inside so that it runs faster. Okay. And obviously in the backend, it's using C++. But then other part, which I already discussed with you yesterday, that what if we use C++ codes and compile them? Okay, already compile them, because here it was not compiled code. It was interpreted line by line. Obviously, that you understand that it will take longer time if you do like that. Whereas if you already compile the same code, same function, as you can see, I have written two, all these codes are there in the repository, in the GitHub repository. So if you create these two, one is the header file, one is the source file, these two files. Here I'm declaring this box, this cell of this Jupyter notebook as the bash cell. That's why I can run these bash commands. As you can see, obviously, these are not Python commands. Cat is a bash command. So just to show you what is inside these files. And as you can see, the first file, which is the header file, it has the declaration of the function, which is optimized largest sum. And in the source file, which is this analysis.cxx, that is this, again, the same function is written inside this, this file, which we already saw before. Now, what we are doing is using G++, which is a C++ compiler. What we are doing is we are compiling these two codes, analysis.hxx and analysis.cxx, and we are creating this shared library, right? So this is .so. We are creating this file from this analysis.cxx. That means we already compile and create the object file, which is what the computer knows, the CPU knows, the object, like the translated machine level language, right? So then what we are doing, we are loading. So here, this is again an interpreter command. As you can see, include analysis.hxx. Basically, whenever we write something in C++, you already know that we have to include the header file, because the function is written inside the source file, but still we have to load the header file to declare the function. And then also there is a method called load of the root G system. And this basically loads this shared object, which we have created after compiling the code. And then you run, you see, root.optimized largest sum, right? And if you run it, you will see that now the time reduces to about 2 microseconds. So it was, if you just use the interpreter, everything is PyROOT, except obviously one part was Python. So except that everything is PyROOT. Whatever we are doing is using Python, but inside Python, we are trying to access C++ facilities. And as you can see, we went from 40 to 2, right? We went from 40 to 2, right? And whereas that means 20 times reduction. Whereas using normal Python, it takes about 700 microseconds. And this will scale up, obviously, with more data, right? So that's the reason why we would still like to use C++, right? We don't want to do everything in Python. Obviously, so I will come back to that again, but let's go back to the slides. But this is the answer to Ovik's question. If you have more questions, you can ask. Otherwise, I will start discussing about uproot. Okay, so let's start. So I gave you a hint already yesterday that what uproot is. Basically, it is kind of a, at some point people thought, when people started using all these Python libraries for machine learning and all kind of data analysis work, as I already said, that the machine learning community or data analysis community, they mostly use Python. And as they mostly use Python, many people know Python and they write back, many packages are available. I mean, maybe in thousands of packages are available which are written in Python. So in PEEP or conda, you will see that there are thousands of packages with different use, right? So if we want to use this vast, collection of existing libraries, which are sometimes not available in C++, because as I said, there is more people working in Python than C++. So it is more popular, and because there are more libraries, any language is more popular because of their libraries that are already available in that language. And people can use those libraries without writing them from scratch, right? That is what we want to do. I mean, if you want to do some fit, let's say to an often histogram, as I have shown, we don't want to write a whole framework to do the fit. We would like to, because that is not our final goal, right? Because our final goal is not to create a package which will fit a histogram. Obviously, if it is our goal, obviously we have to do that. But our goal is to understand the data and try to discover new particles, let's say. So as I already discussed yesterday. So, and if you want to discover new particle, you don't obviously want to write C++ or Python packages. I mean, unless it is necessary. So that's why we rely on all the existing packages that are there in the world. So, and as I said, that as most of them are in Python, so it was mandatory that people could convert a root file where we have all the data stored, to convert that to Python objects or Python data types like Python list, NumPy arrays, and etc. So that was the main idea. And for that, uproot came and tried to do this conversion. So he tried to read the root file, read the trees from the root file or the histograms of the root file. Obviously, you do not, in contrast to PyROOT, uproot has no dependence on C++ root, okay? So even if you don't have root installed in your computer, if you only installed uproot, you can still open a root file and do whatever you want to do, okay? Obviously in Python. Then you will lose all the features of root which are existing. I will come to that point later. So, and obviously when you read the tree, let's say, you will convert them, as I already said, convert the blocks of data into NumPy array or pandas data frame, or let's say there is something new for high energy physics, which generally outside high energy physics is not used much, which is called awkward arrays. I will not go into the details of that. but I will just touch upon it so that you can understand what it does. But still, so you have to convert basically the C++ objects that are stored inside root into Pythonic objects, right? And then do all the machine learning stuff that you want to. I will come to that. So the basic difference between root and uproot, as you can see, is PyROOT and uproot is PyROOT is based on root. It accesses all the features of root, existing, features of root, which are written in C++. Whereas uproot has no dependence on root except and it is only used for reading and writing the file, not more than that. And because of that, that is the downside of uproot. Another downside of uproot, obviously the first one is that it is it does all the manipulations in Python, and it can be slower, as we have already seen. Whereas PyROOT uses the C++ classes of root, that means it is much faster. But yeah, obviously uproot tried to improve that by using awkward arrays. As I said, awkward array is something which are kind of NumPy arrays, but it at the back end, it uses C++ to manipulate the arrays. I mean, NumPy does the same. I mean, any Python obviously have to have some either C or C++ backend. But still, so they tried to make it faster than NumPy by using awkward array, which uses C++. But still, obviously, then you will miss all the other facilities that you have in root. Like you want to create a histogram, let's say. You can't do that using uproot or awkward array. For that, you have to use another library, which is called Matplotlib or Hist, or there are many libraries which can be used. And also, if you want to do analysis, here you can write your own script in PyROOT, and you just, as we saw already, that we create a tree, we create a root file, and we can store something in the root file, or we can read the root file, we can make some analysis, like apply some selections on px, py, we will see. So all these kind of things can be done just using just using PyROOT, whereas uproot cannot do that. Either we have to use awkward array, panda, NumPy, these kind of libraries to do those kind of things, or there is another framework which is common in high energy physics right now, which is called COFIA, which basically does some high level analysis on top of the arrays that you create using which you get from uproot. Basically either awkward array, pandas, data frame, or NumPy array. These kind of things, these kind of objects are analyzed using COFIA. So this is basically the way uproot works. And as you can see, you need much more number of libraries if you use uproot. Whereas all these kind of things, starting from analysis to histogramming, like visualization of your data, and selection, processing, everything can be done using root. So you need only one package, root, to use PyROOT. But whereas if you use uproot, you need many other packages. But then what is the benefit of that? The benefit is that it is true that some people would like to use one package because they learn one package and they try to use that for whatever purpose they want. I mean, they would like to use like that. But some people who are slightly different, and they want to use whole lot of packages and try to see which one is better, or which some people have some preferences, that why should I always produce all those histograms which looks like same, because they are all made from root. I would like to use some other kind of package which can produce some better histograms or better visualization, and etc. So this kind of flexibility is there if you use uproot. But obviously, if you use PyROOT, you can still do the same now, because it's not that if you use PyROOT, you cannot use hist, or you cannot use panda or awkward array or NumPy. We will see that we can also add them. And okay, I will come to this later. But before that, I would like to start the exercise. If you have any question, please ask while I'm going to the repository. Okay. Okay, I see no hands raised. So then I will directly go to the first example. So you have already seen how I could load the root file that I've created in exercise 1 using PyROOT. So I loaded the file, and I was trying to access the data inside the file. The same thing obviously is possible using uproot, and that is the purpose of uproot, right? So it basically reads the file, as you can see, and I can show you just to give you the contrast between the two. Where is that? Okay, let me open it again. Just to give you the difference, tell you the difference between the two. So you remember that using PyROOT, what we were doing this root.t file, and then name of the file. And this time we were just trying to read it. We didn't want to create it. So that's why we said read. That means whatever you do now, this file will remain as it was. You cannot change the data inside the file. But obviously, if you want to change it, you have to do recreate, right? As we did yesterday to create the file. So, okay, sorry. And then the way we are opening the file using uproot is just simple as uproot.open and then the name of the file. Okay, so this is by default, it's going to open it in reading mode. That means it's not going to create this file, but read this file. And then what you can do, okay, let's run it. So I imported uproot, then I loaded the file, and as you can see, we get this file, and now this file is a Python object. It's not, it is not a proxy. It is not connected to any C++ object in the memory. It's pure Python object. Okay, so and as you can see, I mean, if you want to look what is inside this file, like in Python, Python dictionary has this method called keys, which will return all the keys of the Python dictionary. So it's the same. You can call keys for the file object that you have created from uproot.open. And this is returning only one object inside or one key inside, which is called tree, right? So let's look at what is file. You can also do this. So this is okay, something like this, which is totally Python. And then you can do file.class names, which will return the class names. But then, as you can see, this tree, which is inside the file, the name of the class is TTree. Then you can ask, oh, that does it mean that this uproot or this object, which is called tree, is it a C++ object like before when we used PyROOT? The answer is no. Then you can ask, why does it call it TTree then? It's just the way uproot is implemented. So it can sense while it is reading the root file, it can already get the C++ types of each of the objects written inside the file, right? So it is storing those types somewhere, but it has nothing to do with TTree. Like if you run on this tree, if you run let's say what we did with this file, let's say. So what we did tree.print, right, in PyROOT, because it was still a TTree. That's why we could run this print method of TTree in root. Can we do the same here? Let's see. So let's not do this, but do this print. Because if this object is a TTree object, then it should have a print method. But as you can see, it's complaining. It's saying that there is no print method. Okay. So because it is not a TTree, it is not the C++ TTree or root TTree. And that's why they have defined all kind of methods to these kind of objects. Let's say when you read the tree from the file, which is obviously a Python object, then that Python object has this show method. Okay, and this show method will give you kind of the same table as you had when you use PyROOT, right? So it is the table that you got if you run tree.print, right? The same thing, but here you see that the type of these variables that you stored inside the tree were shown, and they were all C++ types: vector of float, vector of float, vector of float, right? Whereas if you look at the uproot, here it says that these objects originally were vector of floats, but they are no longer vector of floats, obviously. They are interpreted inside Python as jagged arrays. Okay, jagged arrays, which are kind of an object of awkward. So by default, PyROOT, not uproot and awkward, they come together. So that's why whenever you install uproot, you will see that awkward package will also get installed. Okay, so what we are looking here is that somehow this uproot is translating this std vectors into jagged arrays of awkward, which are totally Pythonic. But then obviously, as I said, that awkward, these jagged arrays, in the backend, they're using C++ or C to do all the manipulations. But still, it's not C++ object. That's to be remembered. And as you can see, these are the interpretation of the objects that are there in the tree. So this is exactly what right now this PX means. A PX is a jagged array. Similarly, PY, PZ, and energy. You can get the type name. I mean, you can get all these information separately for each branch, let's say, or in this case, they are called columns, but whatever, arrays. So this, you see, if you do T and then inside bracket PX, that is going to return the array. And then if you call type name method of this object, it will tell you the original type of this object. That means the type of this object while it was written in C++. But if you want to check how it is interpreted in uproot, and as you can see, it is jagged array. But then, as you can see, I can take the array, okay, from the tree and save it in this mypx object. So mypx is now an array. And if I look at the type of this array, it says it is awkward high-level array. So it comes from this class, which is called awkward high-level array. Now, just a few words about awkward. So as you saw, mainly in high energy physics, the data sets are slightly different than the data sets that are used in general in machine learning or data science community, where the data structure is rectangular. I mean, you have for each event or for each let's say, for example, if you are trying to if you are trying to predict the price of a house, in a region, okay, and for that you have, let's say, multiple information of each house, okay, how many story, what is the area of the land on which this house is built, what is the location, and many other features. So all these things, for each house, the data set that you have, that means the information of individual houses, each house has the same information as the other. Yes, it is true that for some house, some information may be missing, but still the whole data set looks like a rectangular data set, a table kind of. But whereas in high energy physics, we know that each event you can compare each event with one house in the other data set. So here in each event, you have electrons, you have photons, you have muons, but these photons, muon, electrons, they may not be of the same number as in other events. Like in one event, you can have 2 electrons, but in another event, you can have 0 electrons. So that means if you have, let's say, an array, okay, of electrons, then you will see that in one event, that array is not filled, but in another event, that array is filled twice. In another event, that array is filled once. So the number of elements in the array, that means the features in the array, that vary with event to event. So that means it is not a tabular data, or it is not a rectangular data. Okay, so that's why this term jagged array comes, because generally when we define arrays, we generally think that they have equal length. Okay, so each array has equal length. That is how we generally use NumPy or pandas data frame, where we expect each of, let's say, the columns have one element. Whereas, and also you have all the columns filled for each event. But now in high energy physics, you have columns, but each column is not filled by the same number of elements for each row, let's say. It can be filled twice, thrice, or even it may not be filled in one row. So that's why it is called jagged array. And generally in high energy physics, that's why this awkward package is used. And as you can see, this is a jagged array, and I can also print this. So let's say print my px. You see, I mean, you remember that we had, okay, so let's print up to 5th element. Okay, no, 2. Okay, so the first 2 elements of this array. And as you can see, the first element is filled once, the second element is filled twice. That's how we created the root file, right? Created the tree. We filled it once for the first event, filled it twice in the second event. So this is the reason why it is jagged. As you can see, the first event has different number of elements than the second, but they correspond to the same variable, which is px in this case, but they have different size event to event. That's why it is jagged. Now, okay, so this I wanted to, okay, so what you can do again, you can get the py from the tree, but then you can say that I don't want to take all the data at once, because then if you, let's say, if you have millions of events, in this case, we have 1,000 events, but if you have millions of events, then if you load everything in one array like this, it may not work. It can blow the memory, because at once you cannot load the whole data set that you have. That's also another cons of using Python. But yeah, still we can do that. And then again, we can do all kinds of things that we do with arrays. I know you have learned about Python arrays, NumPy arrays, and etc. So the same thing can be done. You can use length to know the length of the array. And here I'm taking the 0th element of my pi. And as you can see here, what I'm saying is I want to take starting from 10th to 20th event. I don't want to take everything. I want to take from 10th to 20th event. And then that means that the first element will be the 10th event. And this shows the number of elements inside that 10th event, how many elements of that array is there. Okay, and then similar to what we did with PyROOT or root, we tried to plot this, right? So here, as I said, that uproot cannot do that. So for that, we have to use another library. Maybe we can use Matplotlib, because hopefully you have seen some examples of Matplotlib already in the Python lectures. So that is what we are using here. So Matplotlib. So what we are doing is we are taking X, but only from 10 to 20. We don't want to take everything. But obviously, it is a jagged array. That means each element has different number of different lengths. So you cannot plot it directly using Matplotlib. Matplotlib only takes an array. It cannot take arrays of array, or it has to be a flat array, right? So that's why what we are doing here, we are okay. Here, what I'm trying to do is, first of all, before going to that, I'm converting this jagged array into a list, normal Python list, without this jaggedness, so that you do not have, but yeah, you are obviously that means you are combining all the PXs that you have in events from 10 to 20 into one single array, right? And then, so that I'm storing into PX branch, but PX branch is obviously a jagged array already. And I'm taking the first element of this PX branch. So we can print it if you want. So PX branch, 0th element. And this is what it is. So it has all these values of PXs, right? And I'm just passing this to the Matplotlib pyplot, and I'm calling this hist method of this, or hist function of this plotter library. And then I'm passing the name of the array and how many bins I would like to have. And there are many arguments that you can set, like I'm setting some label, which is PX, and the type of the histogram that I would like to see is a step histogram, which is similar to what we saw using PyROOT. So we saw this histogram. So the same thing we are trying to do, but using uproot and Matplotlib. And as you can see, this is what I get. But obviously, I couldn't load the whole data inside the memory, which is also something bad, right? Because here, why couldn't we do that? Because here, when we say, okay, load the whole data into one array, what we did here, we were doing it at once. We are saving everything that is there in the tree into one array. And that array can be very big, and that can be the problem. So that's why we had to reduce the size of the array by setting some starting and in the stop point. And then we are plotting it. But in case of PyROOT, you saw that we were trying to do this event loop, and in each event we were passing some filling the histogram with one value, and at the end we are not converting all the information that is stored inside this tree. We are not storing it into one object. Every time for each event we are just looping over this tree and then filling it. But okay, some people can say that this is more time consuming. And also, as you can see here, we didn't do any kind of loops over all the events. It's so straightforward. You just write my py dot equal to tree, then py dot array, and it will return you the whole array. So you have no loop over all the events, right? Which is why it is so compact. Obviously, this loop is there inside, and that loop is done by uproot. Uproot is reading the dataset and then converting it into an array. So this loop is somewhere there inside, but we can't see it from outside. It's very compact, one-line code, which basically does the same thing that we did using PyROOT by looping over the events. But then question is, okay, so then we got this plot. I'm not going to, okay, just two more things that I would like to say. So here you remember that we were taking only one variable from the tree. We can do, we can load everything at once. Like we can say, okay, I want to take all the branches of the tree as NumPy arrays inside the new object, which I call particle underscore NP. Okay. And as you can see, this particle underscore NP becomes one NumPy array. Okay. And before it was awkward by default. But if you say that library equal to NP, which is the standard standard way of calling NumPy, if you say NP, then the array that this tree or T object is going to return is the NumPy array. So you can, if you want, you can, sorry, if you want, you can print this part NP. Okay, but it's as you can say, it's going to take a long time because yes, look, it has exceeded the volume of data. So maybe we can reduce it to 2 just to see if it works. Yes, it worked. So as you can see, this is the problem, that you try to load everything inside the file and it doesn't work because it exceeds the size of the object. So, but still, as you can see, this is a NumPy array. Each of these arrays are, as you can see, NumPy, and you can also see the data type, blah, blah. So data type is float, as we already saw. So, okay, this is how it is done. And also you can save this array as panda data frame. Let's do part pd dot, I think so. I don't, okay, not so. What happened? Okay. Okay, again, the same problem probably. So let's do it for 2. No. Okay. It's probably not working because I will look into this, but it's probably not working because you have this jaggedness in your input data set, right? And which pandas doesn't know. That's the problem. But obviously another thing, which is something called awkward pandas, that you need to get such data frame where each column has elements of different size or arrays of different size, which the normal panda cannot read. So that means you need a whole lot of libraries if you want to use this Python packages. But again, it gives you more flexibility. That's why people use it. Now, I would like to come and I mean, obviously we will finish soon, but I would like to go to the next topic, which we wanted to discuss today, which is the advanced use case of PyROOT. Okay, so which I have here in something called exercise underscore Higgs diphoton. Okay, So as I told you that I will give you an example, which is kind of exactly the way we do the analysis in CMS or Atlas experiments. Okay, I see some question. Let me see. Okay. Can we use part underscore NP is equal to NP dot TRAs? Right. Yes, we are doing, instead of this, what you would like to use NP dot, no. Why would you like to use NP dot T dot arrays? No, it's not like that. Obviously, it will not work. You can check it. If you run it like this, it will not work. So, oh, somehow this chat window is not visible to all of you. But okay, I think yes, you can see in the chat box. No, it's not going to work like that. But yeah, if you want to convert the array in a different way, it's possible. You do not need to always define this library equal to NP. That is not the only way to convert. So you can first get the awkward array, and then you can convert the awkward array into NumPy array. Okay, but obviously, as you can still you can understand, like for the pandas data frame, as we couldn't convert directly that tree to pandas data frame because there was a jaggedness in the arrays. So same thing will happen with NumPy also, because NumPy will not be able to understand the way the data is stored. So it will complain. So if you want to do that, either you have to have same number of elements in each array, and then you can add it to NumPy, or you can make a flat array without this like event structure, event by event structure. You can make a flat array and pass it to NumPy, and then it will understand. Okay, so, but yeah, so, okay, let's go to the next topic, which I wanted to discuss. So here, what we would like to see in next 10 minutes, obviously, I'm not going to ask you to run it here because it's going to take some time. Obviously, you can run it later after the class. But now it's time to understand what is being done. And it's a bit complex. As I said, it's an advanced example of PyROOT. But one important feature that I would like to show you, which I'm using here, which is called R data frame. So you have already, probably some of you have already have an idea what is a data frame. If you don't, you can think of it as a table, right? With some number of columns, some number of rows, okay? But yeah, you can, but it is kind of, why we want to use data frame structure but not tree structure, because you remember that I told you that root uses tree structure, whereas most of the machine learning community, they use data frame structure of data. The reason, obviously, there are many differences in the data structure, as we already have seen, that the jaggedness of the arrays and etc. But still, people who are familiar with Python and familiar with this kind of array, syntax, I mean, hopefully you have learned in your Python course how to play with an array, a NumPy array or pandas data frame, So these features are very, very, I would not call it features, but this kind of syntax is very useful because they are very compact. You probably have seen that you can define a NumPy array. We can do it for in short. I can show you. So you remember that you can define a NumPy array. Let's say array is equal to np dot array, and then you can say 2, 5, 7, 8, right? Okay, NumPy is not defined. Okay, I can define it here. Import NumPy as np. Right now you have this array. Okay, Okay, and then you can do all kind of manipulation, right? So what you can do is print. Okay, I can do in the same place. You can say array greater than 2, let's say, right? You can do this kind of manipulations of the array. So this is so like this is the reason why we would like to use arrays, that you can just write one line as if you are applying a selection on one variable, whereas this is not a one variable. This is a list of values. This variable has a list of values, but you are saying AR greater than 2, where AR is not a single number, it's a list. But still you can compactify the whole thing. That means you loop over each of the values, and then you apply this selection that each of these values has to be greater than 2, and then you return a boolean which is 0 for if it is less than 2, and it is 1 for if it is greater than 2, and then using that boolean you get this output, which is 5, 7, and 8. So all this whole process that is running at the back end is not visible here, and that makes the code very compact, and you can easily find errors if you have done such error. I mean, if you have nested for loops and etc., as you can see, I mean, you can that is the benefit of using Python. So it's so simple to write the code. That's basically why we want to use arrays. Okay, so now I'm moving to this. So our data frame is kind of it is a feature of PyROOT or root, you can say, and but using this R data frame, we can have the same functionality that we have with pandas data frame or arrays, NumPy arrays, let's say. So we can do all those kind of manipulations that we can do with NumPy arrays or pandas data frame. So in this example, what we are trying to do, as you can see, first of all, we are trying to access some open data. I'm sorry that I would like to take a few more minutes because probably it's already the time to finish today's lecture, but still I will take 10 more minutes to finish this. So first, what we are doing here, we are trying to tell that where my data is located. And as you can see, this is accessed from a server at CERN, which is a public data set. Anybody can access that data. And what we are doing, if you have installed root, as you can see, if you have installed root, and root has this art data frame class, which can read the files inside this directory, which are somewhere in the world, but you are running it from your machine. But still, as that those files are accessible publicly, you can run it like this. So what it is doing, as you can see, this is a one-liner. Again, this is a benefit of using Python, that you can make a for loop, but inside one line. So for X in A, B, C, D, you run this. That means in this curly brace, basically this will be first replaced by A, then replaced by B, then replaced by C, then replaced by D. That means here there will be multiple strings, which are the names of the data sets, basically. So data A, data B, data C, data D. These are the real data taken in 2016 by Atlas, which are stored as a public data set. So many people, they would like to use these data sets and they want to play with it. They want to look if they can find Higgs. They want to do some machine learning, applications on these data sets to find something which maybe the other researchers who have used these data sets already, they have missed something inside the data set. But you have the access to this public data, you can analyze it, And if you can find something new inside. So, but okay, today what we would like to do is we would like to discover Higgs, which is already discovered, but you can generalize it to something else if you want. So what we are doing here, so we have these files, and the first set of files, as you can see, I create a dictionary in Python, which is called df. Okay, and this dictionary will contain R data frames. So each of these root.r data frame is actually going to return an R data frame object, which is kind of a data frame, you can call it. And that data frame will be stored in this key. So every dictionary, as you probably know, that every dictionary has some keys and some values, right? So what you are doing is you have this data key, and corresponding to the data key, you have some number of files or R data frames. Similarly, you have GGH and VBF. For the moment, it's not important what they are, but they are, I mean, just for people who may know how the Higgs is produced at LHC, they know that that can be produced by either gluon-gluon fusion or vector boson fusion. I mean, there are many other ways to produce Higgs at LHC in proton-proton collisions, but these are the main two main processes, production modes of Higgs in LHC. So basically, you have some simulation, as you can see, MC, Monte Carlo simulation. So these are the Monte Carlo simulated data, which are also public, and you can access in the same directory, from the same directory. And then you have this, oh, okay. I thought I already ran it, but okay, maybe I didn't. So I don't know if we can finish this. Okay, at least I have the final plot. If not the each of the blocks. So then what you do is you can, again, as df is a dictionary, you can get the keys of the dictionary, and you can make a list of those keys and put it inside the processes. This is for some purpose, which is not important here. Some manipulations that we are trying to do. But then one important feature of these R data frames are something called define. So what it does is it is going to define a new variable inside this data frame, new column. Basically, a new column will be added inside the data frame whose name is weight. Okay, I want to create a new column whose name is weight. And what that column will be? The column will be the product of the values saved in other columns. Other columns in the sense there are inside these data frames, there are existing columns, obviously. It has some data stored, of course. And there are many, many columns. And out of them, there is one column called scale factor photon, another column called scale factor photon trigger, another column called scale factor pileup, another column called MC weight. Okay, so I'm not going to explain each of these, but these are some kind of corrections to the Monte Carlo, as you can see. But okay, I would not go deeper than that. So this weight column is created by taking the product of all these columns that are already there inside these files. Okay, and then okay, you get the new data frame, R data frame, which has an additional column called weight, and that is how you define it. Similarly, for data, this is done only for Monte Carlo, but for data, you also define the same column, but that column for all events in data has only one value, which is 1. But as you can see, each of these, if you want to do the same using normal PyROOT or normal root, you have to loop over all the events, and for each event, you have to multiply the values of each of these variables and then store that variable, weight variable, inside the tree. And that is how we do it generally, that looping over all the event. But here, That is why it is called columnar analysis, because we are actually playing with the columns. We forget about the rows, the individual events. What we are doing, just by saying that multiply this column scale factor photon with scale factor photon trigger with scale factor photon pileup with MC weight, all these 4 columns. When you say multiply 4 columns, what does it mean? It means that it is going to multiply each of the rows, right? But do you see such code here? No, that is done in the hindsight. It's going to loop over all the events, going to multiply, but that is the benefit of using Python, that you just write one line, but you do not need to write all those 100 lines that you need to do just to create one extra branch in the tree. So that is the benefit. So it is one line and you just manipulate with the names of the columns. As we saw with NumPy also, we just say array greater than 2, that will remove all the elements of the array which are below 2 or equal to 2. So that is the benefit of using array. And that feature is also integrated in root, and you can use it in PyROOT also. Then what we are doing here, after that, we are using another feature of our data frame, which is called filter. What does it mean? It means that you are going to pass some argument in this, let's say, function, and that argument should be Boolean, which will tell us that which row to be kept and which row to be thrown away. Look, and this trig P is another column inside the original dataset, okay? Which obviously at the moment we didn't see at all the columns that are saved, but still imagine that this trig P is another column in the R data frame, okay? And then and that trig P contains Boolean. That means for some events it's 0, some events it's 1. Okay, and when you say filter and then you pass the name of the column, just the name of the column, what it does is it throws away all the rows where this trig P is 0. And again, I mean, please stop me whenever you have any doubt. Okay, so and then what you're doing is now the new R data frame that you have doesn't have those rows where this trig P is basically the trigger. So we, as you know, I mean, in LHC, we can't record all the data, but we have to use some trigger. That means we have to throw away most of the events which we already know, the physics of which we already know. And we want to store only those events where we think that there can be new physics. So that is why we use trigger. And obviously, we would like to do the same for Monte Carlo also. So for data, both data and Monte Carlo, we throw the events which couldn't pass any trigger or photon trigger in this case, as you can see, because we want to look at Higgs to diphoton kind of events. And obviously that means we would like to see only those events where we have photons, because if in an event there is no photon, I mean, we can expect that there cannot be Higgs to diphoton process. So that's why we filter with this trigger, and then we apply more. We can see what it is doing. So this trigger P was already an existing column inside the R data frame, whereas we can create new columns, as we already discussed, by using this define function method of R data frame. And then this new column can be a Boolean also. And that means what we would like to do before, you remember that we took the product of multiple other columns. But here what we are doing, we are using those column names, just using column names, but then we are applying selections on those columns. As you can see, there is one column called photon PT, and we are saying that if the photon PT is above 25 GeV, because the value which are stored inside the column is in MEV. So that's why it is written 25,000 MEV. So if the photon PT is above 25 GeV, and if the photon is kind of a good photon, I mean, this I'm not going into the detail. This is a machine learning part, which I'm not going to show you today, maybe tomorrow. And then there are some other selections on different columns, as you can see. There are more selections and etc. And at the end, after that, there will be some events, obviously, which will pass this selection. And then you, on top of that, you can apply some filter. As you can see, you are defining a variable which is called good photons. But after define, you can append this filter function on top of the object that this define is going to return. This define is going to return another R data frame, right, with the new column, these good photons. And now what you are doing, so now you got the new R data frame with good photons, and then you are applying selections on that good photons. So you are saying that if the sum of good photons is equal to 2, that means this is basically, okay, it was not a Boolean, but it was an integer. And what it represents the number of good photons in that event. And as you can see, as we are trying to find Higgs going to 2 photons, we want to make sure that there has to be exactly 2 photons in the event. Only those events we are going to consider. We are not going to consider other events where we have 3 photons or where we have 1 photon or 0 photon, because those events are not Higgs-like events, Higgs to diphoton-like events. Okay, so you apply such selections, and I'm not going to go through each of these selections. This is just for you to play with. I have just kept this example or exercise here to show you what can be achieved by using PyROOT, and also obviously with Uproot. But for Uproot, you have to use other libraries. I will talk about them later. So you use some other columns and make some, as you can see, you can make some selections based on other columns, based on other features of the columns. And you can, as you can see, you can concatenate like different methods one after the other. So like use just the way we do in Python, right? So we can take sum, and then we can take average, then blah blah. So anything that we can do with Python arrays, what we are doing here is similar, or also with pandas data frame. Then, as you can see now, until now, everything was written in Python, and then we are going to use something C++ in the middle. Why? Because one reason can be that suppose you already have one function which you wrote in C++, and you do not want to repeat, you do not want to write it again in Python. And also there are also another benefits, some other benefits, like if you write something in C++ and you want to use it, it will be faster, right? As we already saw. So that's why what we are doing is we are defining a C++ function, which is, what is that? It is basically going to construct the invariant mass. Invariant mass from what? From vectors of PT, eta, phi, and energy. As you know that if you want to create Lorentz vectors or 4 vectors, you need PT. You can have PT, eta, phi energy, and using that you can create a Lorentz vector or 4 vector. And root math library already has this kind of feature, which is called PT, eta, phi vector, phi e vector. That means a vector which has these 4 variables, PT, eta, phi e, and you are creating an object called P1. Again, this is a C++ object that you are creating. And again, you can, so PT is a vector, rvec f. It means it is a root vector of type float. Okay, so that means in this vector, float is stored. And this rvec_f is a data type inside root. Root knows about this data type. Okay. So this is a vector. This is a short form of, you can say that this is a casting of a data type, which is a vector, std vector of float. You can, as you know, that we can cast the names of the data types. So it is done here. So rvec_f, and then so then this pt is a vector of floats. And let's say for each event, as we have already removed all those events where we have more than 2 photons or less than 2 photons, we only keep events with equal to 2 photons. So that's why this pt will have 0th element and the first element, first photon and the second photon, right? Each of these, they will have the first photon and the second photon. And what we basically want to do is, using this function, we want to compute the invariant mass of the 2 photons that we have selected. And for that, there is a method called mass of this pt eta phi e vector of root. And we are calling that function to get the mass of the sum of these 2 vectors. And we are dividing it by 1000 because what we get here will be in mega electron volt, and we want to convert it into GeV, giga electron volt, right? So that's why it is done. And same, so now, another interesting part is, now look, this compute invariant mass function was written in C++, right? And what you are doing here, you are defining a new column, which is m_yy, which is m_gamma basically. So the diphoton invariant mass. And what you are doing, so look, you are passing another string that is compute invariant mass, which is the name of this function, and you are passing the arguments. Like you are passing the first element, obviously the first argument should be the pt. So what you're doing, photon_pt, and then you are passing the Boolean good photons, which was like, it has to be equal to 2, right? So if you pass this to photon_pt, it's basically, it will return a vector of float with 2 elements, right? And then similarly for photon eta, photon phi, photon energy. And then what this is going to return, it will return the invariant mass, and that you are storing in m_yy, which is another column in your data frame, right? And then you are filtering your data frame again by applying some selections. You are saying that, oh, if the as you can see, you convert this pt into GeV, and then you're saying that if the photon pt divided by the mass of the 2 photons is greater than 0.35, or if the second photon pt, this is the first photon 0 and this is the second photon pt, divided by the m_gamma is greater than 0.25, then I will throw those events. So for all these conditions, I will throw the events. Keep the events. Which the condition, if these conditions are not satisfied, that means for those events where these conditions are not satisfied, they will be thrown. And only those events where this condition is satisfied, they will be kept inside the data frame, right? And then similarly, also you want to keep only those events, because now we know that Higgs was found at 125 GeV, right? So that's why we want to keep those events only for which the invariant mass is between 105 to 160, right? So again, you are basically throwing everything that you don't want to have, and you know that where your Higgs is sitting. So that's why you can apply all this selection. And then this is as easy as this to create a one-dimensional histogram using, let's say, from the R data frame. So this df and then p, this is, I mean, as you can see, every time we are looping over processes, And then when this df, this p is a string, right? You remember that this processes has either it is a data or ggh or vbf. Okay, so these strings, and that means you're passing the keys every time, and this df is a dictionary, and then when you pass this key to the dictionary, it returns the value, and the value is our data frame, and that our data frame has a function called histo1d, right? And if you are, or you can call it a class, whatever. So, but what it returns, this R data frame has a function which is histo1d, and if you call that histo1d function, it returns a th1, the root histogram basically, which you are kind of storing in hists, and hists is another dictionary that you have created, because for each process you want to create one histogram, right? So that's why you see here that hist is a dictionary like df, data frame. These are dictionaries, and for each key, that means either for data or for Monte Carlo, you store the histograms. And how do you create the histogram? As you can see, this root r data frame dot th1d model. So this is the way to create a th1d, the one-dimensional histogram with doubles. Okay, and what you are storing there, you are storing, first of all, this p is the name of the histogram. Okay, and what is this p? P is obviously the name of the process, either it is data or ggh or vbf. So you are creating one histogram which is called data, one histogram which is called ggh, one histogram which is called vbf, right? And then you have the title of the histogram. Okay, and this is how this th1d is created. So you have the name of the histogram, title of the histogram, and not only that, you can already pass the x and y axis labels. Like here I'm passing m underscore gamma gamma gv, and this is going to be converted using LaTeX. As you know, I mean, in LaTeX, if you do m underscore second bracket gamma gamma, it's basically will show m with a subscript gamma gamma, right? So everything can be done inside this one line, right? And then you have this number of bins and the range of the histogram. So each histogram is created for 30 bins between 105 to 160, because that is the selection obviously that we have applied. And what we are going to store here, this is important. What we are going to store is this m gamma gamma variable, m underscore gamma gamma variable, that or column that we have created already, we have defined. So we are going to we want to store or fill the histogram with the value stored in this m gamma gamma. With, as you know probably, that histograms can be filled with some weights per event, because it's not that all event has the same weight sometimes, but which is a very which can be for you it can be a jargon, but basically we apply some weights to each event to fill the histogram. But as the main purpose of showing this is that, look here, there is no event loop. You are not doing any loop over events. So, but obviously it is done in the hindsight, but while you write the code, it's a single line which does everything for you. That means it will go through all the events, and then one by one fill the histogram with m gamma gamma variable, and at the end it will return you the hist. Okay, and then okay, at the end, okay, so this, what is this? This is basically whatever we have done until now. This is a good part again, and which is different from this and what we have seen using uproot, that we couldn't load the whole data set at once. So this is called a lazy arrays or lazy data frames, the way of handling the data frames lazily. What does it mean? It means that when you run this let's say script, all you have done here is basically you have created a graph for our data frame. Let's say what it means that you have created a new column, you have filtered some events, you have defined a histogram, etc., etc. Everything that you did was not physically accessing the data. It was not accessing the data at all. It was just storing all the steps that you ran until now. It was just storing them somewhere. As you can see, each of these instructions that you have given, like define function, they are a set of strings, right? So these strings are saved somewhere. And when you run one by one all these lines, basically a graph is being created where each point of the graph knows what to do there, but it only stores the instructions. It doesn't process the data. Okay, it just stores the instructions. And then only when you call, let's say, run graphs, okay, and obviously there are other ways of computing the graph, but still this is one way. So only when you call run graphs, then it's going to process the data. Okay, it's going to load the data and process it and do whatever you asked. But before that, it's not doing anything. But what is the benefit of that? The benefit of this is that every time, let's say you are converting, you are applying some filter and saving it into one Python object. And then again, you go and apply another filter on that Python object. Then you define one column in that Python object. So all this process, if you do one by one, then it may have some issue with the memory, because obviously at the beginning, when you created the first column, you had all the events in the tree. And that means you are loading everything in the tree that you have in the tree, which can exceed the memory limit. But what you are trying to do here is that you do not load everything together, but you give all the instructions what to do, and then you ask this run graphs or some other thing, which basically inside will run this C++ code and return only the end product. It's not going to return you the intermediate products. That means, as you can see, if you say run graphs and then you call hists s, where s goes from ggh blah blah, these processes, it will try to produce these histograms. That's all. But it had all the other columns, and you have applied many selections, you define new variables, but it doesn't care about them. Obviously, during the processing, it did all those. It ran all those instructions that you have provided, but at the end, it is going to return only the histograms. So that means all those data is not going to be returned to you that is there in the tree, which is the benefit of using this. So it is called lazy access of data, kind of. You don't load the data at every time. You load the data only when you need to load the data. And then you can see that as obviously these hists is a dictionary. So you have the method called getValue, which will return the actual original histogram, because that is what the value is for each key of this dictionary. And then you get GGH, VBF data. These are the 3 histograms. And again, I'm not going through this because we have already seen this. We create the canvas and the pad in the canvas. Okay, another part which is interesting is that, again, we are trying to fit. Okay, but before that, I would like to show you the histogram. So this is the histogram that you get. As you can see, these black dots, this is the data. And then you have the dotted blue histogram, which is the background. And you have solid blue histogram, which is the signal. And these are the histograms, and which are plotted on this canvas, which you already saw in one simple example that we have seen, where we plotted some histograms. But then in addition to that, we also would like to see the ratio of, let's say, the data that we have and the Monte Carlo prediction that we have. I mean, only the background, obviously. So this is the ratio. Sorry. And okay, one thing I did a mistake. So this blue dotted line is not the histogram of background. I will come to that in a moment. So that is what I was going to say. It is basically the fitted function. So what generally in histogamma analysis, we try to model the background as a, let's say, falling.
Sir, sorry to interrupt.
Yes.
Can I have an immediate question? Because we know that I mean, after performing the data analysis, we created the maps and then we executed the run graphs, which basically actually loaded the data and give us the 4 histogram which are coming for the 4 different processes.
Yes,
So
you're right.
so we will have 4 histograms
So not
in
4,
which
3
there
here.
will.
In this case, we have 3 process. But yeah, okay, it's fine.
So we should have the histogram you showed, the data is combined. I mean, the data is combined of all 4 processes, or in between there was some code.
No,
and
the
you
data is data.
filter.
It's the real collision data. It's not a.
Okay.
I mean, you do not know if it is the combination of all the Monte Carlo processes that you have. It can have more, but you don't know.
Okay.
But for the moment, obviously, we do not have any background sample. I mean, as you saw, the samples that I have
Yes.
loaded were only
Yes.
only Higgs samples, because we wanted to model the background with a function. And that is what I was going to show, that I am creating here a TF1 object of root, which I'm calling as fit. And then what is that function? Okay, so those who are not familiar with creating functions in root, I would like to explain quickly that suppose if you want to define an one-dimensional function which has only one parameter, one variable, which is x, then all these things in third bracket, the square bracket, which is 0, 1, 2, 3, these are the parameters of your function. That means you can consider this, you can read it like a plus bx plus cx square plus dx cube. Okay, this is the first part of this function. And where this a, b, c, d, they are parameters of your function, right? And then you have e times, I mean, I'm calling this 4th or 5th parameter as e, and then e times exponential minus 0.5 x minus f, where this is another parameter, divided by g, which is another parameter, whole square. So as you can see that this is basically a function where the first part is a polynomial, as you can see, of order 3. And then the second part, which is a Gaussian, right? A Gaussian with obviously mean and sigma parameter, which is 5 and 6. Obviously, 6 is not exactly sigma, but it's square root of 2 sigma, as you know, square root of 2 times sigma. So these are the parameters of the function. That means 7 parameters. So you have created one function which has 7 parameters, and then you start with fixing the values of these parameters. Okay, so then you define some, you say that some parameters should not be changed. It should be fixed. So what you're doing, you're saying that the 6th parameter, which is here 5, the value of that should be 125.0. As you can see, this part of the function is basically, which is a Gaussian, is basically used to model the signal. So what we think is that our Higgs to gamma gamma invariant mass distribution, which is this one, this small one, this histogram, is Gaussian distributed. And we want to model it as a Gaussian distribution. That's why that is the second part of our function. And then we have the first part, which is, as you can see, the third order polynomial, which we call as the background part of our function, of our data. So we want to model the background as a polynomial of degree 3, and we want to model the signal as a Gaussian of degree, a Gaussian. But then what we are doing here, we are fixing the values of some parameters, and then what we are fitting, look, as you can see, we are fitting the data by using this sum of, let's say, background plus signal model. We are using that to feed the data. So data is the data histogram, right? So, and we are fitting it. And as you can see, we have fixed the values of 5, 4, and 6 to 125, 129, 2.39, which we don't care for the moment. Just to say that Higgs mass is close to 125. That's why we think that the signal model should peak around 125 GeV. And we know that the resolution of diphoton invariant mass in CMS or in Atlas, in this case, is about 2.4 GeV. So that's why we already fixed that 2.4 GeV here. So for this standard deviation and mean of the Gaussian. Whereas, yeah, so then you fit the data, and then, as I have shown, that you can draw them on canvas and do different kind of style optimization. That means you add this Atlas open data, square root of s equal to 13 TV, 10 femtobarn inverse. You add the legends. All these things can be done, which are style adding. You can add to the canvas. But most importantly, that you have the data and you fit it with signal plus background model, and then in the ratio you get the difference between the data and the background model, fitted background model. Both of these are fitted, right? So there you get the fitted difference between fitted background model and data, and then you can fit that. Or you can get the difference between the fitted background plus signal model, which is the red, from the dotted blue, which is only the background model. And that looks like a Gaussian, because that is what it should be, because the difference between them is the signal, which is modeled as a Gaussian. And as you can see that we can see the Higgs events. That means we can see some difference between the estimated background and observed data. So this difference between the estimated background and the observed data can be Higgs. If it is, you will learn about this in statistics course, or you already have learned something about this. So from here we can say many things. This is one measurement, and where we can learn or estimate the mass of Higgs. As you can see, this is peaking somewhere around here. So we can say that, okay, the measured mass of Higgs is this, and the uncertainty on the measured mass is some, you can get from the fit, right? So from the fit, you can get the value of the best fit value of the parameter, and also you can get the uncertainty on the parameter, fitted value of the parameter, as you can see here. So all these parameters have some best fit value and some error or uncertainty on them. Though in this case, we have fixed the values of these three because we know exactly how much they should be. But in principle, we can also float them during the fit. And we can see that what is the fitted value of signal invariant mass. And we can see that it will also have some uncertainty like other parameters which are floating in this case. So that's all about this exercise. And we can, at the end, we can store this canvas into one file, and then we can put it in our paper at the end, what we want to publish, right? So that we have discovered Higgs. But the thing is, you can see that within only few lines of code, we can discover Higgs from the dataset. Now the question is, Is it that easy? When Higgs was discovered, the analysis was not that simple that you could write it in one page. Okay, you needed many analyzers and lot of C++ functions and a big framework for that to get this result. But now, with the benefit of PyROOT R data frame, we can quickly do this kind of analysis and produce this kind of results with few lines. That's the power, simplicity of Python that we wanted to have. And obviously, in the backend, we wanted to also keep the performance of C++. So with that, I would like to finish. And we can again start tomorrow from here. Yeah. So if you have any question, please ask. Otherwise, we will stop here. Sorry for taking so much time. I know many of you were, obviously it is expected that many of you were could not follow it properly, but I hope if you, after these lectures, if you go through the code and try to understand them yourself, it will not be very difficult, because that is what was the plan, that I explain things to you, and then such that you can go and read the code and try to understand, and probably you will, it will be at least easier than before for you to understand the codes after you go through this course. Okay, so if you have any question, please ask. Otherwise, we will.
Sir, can I have one quick
Sure.
question? Sir, can you go to the notebook, please? I
Of
just
course.
wanted to know, I mean, obviously it would have been taken I mean, a very long time and lots of analyzer to develop the whole code for the analysis. So my
Exactly.
question is, sir, I mean, it is a very advantageous thing that we create these graphs which leads us to the final signal, and then we can load our data and do the actual analysis on data. But my question here is, I want to know, in the process of creating these graphs, I mean to say, when these sub-modules were developed, so one needs to run it on the data to check whether the things are done correct, or just by writing, assigning the variables, and I mean applying all the cuts and all, one can go with this. I mean, at the back of the Python, it must be looking at the data, some data, and to give output whether the syntax is correct or not. I mean,
Yeah, I mean, obviously, if there is a problem in the syntax or such kind of like common errors, then it will raise some error, right? It will give you some exceptions, and it will stop running. But on the other hand, I agree with you that how will you debug? Because now
yes,
everything
exactly,
is,
yes.
yes, everything is uh, in the hindsight. You are not looking at the real code. You are looking at some
Mhm.
skeleton or some, beautiful face, but you
Yes.
don't know the skeleton behind it. So the answer is yes, of course, this can be debugged, but obviously, whenever you want to debug it, you have to compute the graph at
Yeah,
that
exactly.
point, right? So
That was the question. I mean,
yes,
whenever we want to,
you
yeah.
have to
Okay.
compute the graph wherever you want to know if whatever you are doing is correct or not. So that is why
Okay. Okay.
when you develop this kind of one page analysis, it's good that at every stage, with small number of events, you check if you are getting what you expect. That means you compute the graph after every step, and then see if in the output you see exactly what you wanted to have. For example, let's say you created this weight column using this. Now you want to see, I mean, are these weights are physical, or they are something, I'm doing something wrong? And obviously for
Yes.
that,
Yes.
you can produce the histogram of this weight and check
Yeah.
how the
Yeah.
histogram look like. And then only when you are sure that the weight variable that you have created is correct, it has the correct values, then you go to the next step. You run the next step. You do not run all the steps every time. You run one by one and check every time you get what you want. And then obviously, when you run the next step, you don't compute the weight after this fourth block. Because if you compute the weight there, that means you compute once the whole process. And then if you go to the next step, it will again, until and unless you call compute again, it will keep on adding those instructions in the graph. But still, we don't want to compute the graphs at every stage, because it's going to take a long time in that case. And we will run into the same problem as we saw using Python. So that's why, yes, it can be debugged, but once it is, you check everything using small set of data, then you run it, the whole analysis, without even processing the data, but you run whole analysis. And then at the end, you just invoke the compute command, and then it will return you the final product. You do not need to know what else was done during the whole process.
Yes, correct. That answers my question.
Okay. If there is any other question, I can answer. Otherwise,
Sir, actually, I had one more question, but not related to this, but related to the plot which you showed at the end.
okay,
After
sure.
performing the analysis. I'm not sure. I mean, it's so the bottom panel where you show the signal after subtracting the background. So, sir, a priori, we already know that Higgs mass is going to peak around 125, and we made a fit around 125. But let's say if we were not aware, so we also see a bump-like structure between 140 and 150. If you see the bottom panel clearly, so I mean this is also a kind of looks like a signal for us. So in such cases, what is the best practice or the good practice one should follow? Let's say if we were not aware that yes, I mean Higgs.
Of course, yes, that's true that we don't know. I mean, when the Higgs was not discovered, we didn't know where the Higgs will be, at what mass the Higgs will be, and that is what we wanted to search, right? So
Yes.
yes, it is true that there are different structures here and there. Okay, and when we do the fit, in this case, as we know that Higgs is at 125 GeV, we fix the mean of the Gaussian to 125 GeV. But obviously, generally what we do is we float the mean of the Gaussian, sorry, so that it can fit any bump, as you said. But then the question is, will it fit this bump? Of course, it can. Obviously, that is checked. If you want, you can also check. You can make the mean floating and see where you get the best fit. Okay, so basically what we will see that the best fit will be somewhere here if you define the Gaussian here, not here. Okay, so obviously there can be a Gaussian which is very small, the peak is very small, and that can fit it. But the chi-square or the likelihood that you are going to calculate at the end,
Yes.
that will not be the minimum. Chi-square will not be the minimum if you select a Gaussian there compared to a Gaussian here. Okay, that is
Actually, sir, in chi-square, what we see is, how my fit is deviating from the data point. So basically, it will measure the deviation, the variance of the deviation, and I'm not sure if chi-square, just only judging on the chi-square will
no.
be
I didn't say
the
that. Of course,
okay.
you cannot judge only based on chi-square. But what I said is, suppose if you have only one Gaussian, okay,
Yes.
what you can try is you can just fix the mean of the Gaussian that you have created as signal model, to, let's say, somewhere around 150 or 144, let's say, and then fit it. You will see that there will be a straight line here because obviously there is no other Gaussian. So there will be a straight line here, and then there will be a small Gaussian here. But the question is, the chi-square at the end of that fit will not be good because you see, you can't say that here everything should be flat, right?
Correct.
Now the question can come that are there two peaks? That means can I have two Gaussians to fit?
Double Gaussian fit.
Yes. So that can be a question. And obviously then in that case, what will be our answer? And that is what we do generally, that we sometimes we call it a look elsewhere effect. Okay, which I'm obviously not going to go into the details because that is a statistical process that we like to use to check for Higgs everywhere in this mass range. And only after doing that test, we decide which bump to consider as
The signal region.
the
Okay.
signal.
Okay. So
and you will see that those Gaussians, small Gaussians, will not have any significance in that sense. They will not be considered as, even though if you consider them, they will be almost background-like.
Yeah, I mean, they are
You
not
cannot
physical.
call that as a new particle, basically. You cannot, using this fit, you will not be able to say that even if you use two Gaussians and you fit two Gaussians to these two peaks, you will not be able to say that the second peak is a new particle because that deviation is very small and it is almost background-like. You see what I mean?
Yes. I understand.
But this peak, where you have enough signal, you can consider that to be a real signal because there the deviation from the background is very large. But even then, that may not be very, very large, like may not be 5 sigma. Probably you have heard about this term in high energy physics. It may not be 5 sigma. So if it is not 5 sigma deviation from the background only hypothesis, then you cannot consider also that to be a discovery. Only those fluctuations over the background, which are 5 sigma away, 5 sigma or more away, only then we can consider them as a discovery of new particle. So these deviations are not 5 sigma or not even 1 or 2 sigma.
Recently, there are some papers like people used to plot some Gaussian distribution around 140 to 150 or somewhere else right side. So they are claiming that there is another Higgs.
Yeah,
And,
possible. So that is what we are doing, right? So what we are trying to do is to gather more data and try to see, because the peak that you can see at around 125 GB was not as clear as it is during run 1 of LHC. In run 1 of LHC, it was almost similar to this one, okay? Some random fluctuation. People could say that. But then only when we gathered more data during run 2, this is with 2016, part of 2016 data collected by Atlas, only then we could see a clear bump. So it's possible that if you collect more data, this small bump can raise up and become a bigger bump. And then you can say, that is what I was trying to say, that only when it will become a bigger bump or bigger deviation from your background expectation, then you can confirm that this is a real effect. Otherwise, you can always say that this is just a fluctuation of your background. That's what I want to say. But yeah, it is true that there are people are trying to find more particles in this invariant mass distribution of gamma gamma or other particles.
yeah.
So it's possible, yes. Okay, any more questions? So then maybe I will stop here, and tomorrow we are going to discuss some machine learning applications as I promised. And obviously, I will try to show you a few more things about uproot. And then, as this is obviously one thing that I wanted to show you, so that you have the flavor of what is done in a high energy physics analysis. What can you do using PyROOT? I hope you got some idea. Obviously, not everything. Only when you try yourself, you will learn. But I can only tell you what can be done. But obviously, it is to you. You are going to do it, and you are going to learn it yourself. Okay, so it's not possible to do it. I mean, teach you everything in 3 days. So with that, I will stop here. Thank you for staying so long. And I again request you to go through the examples or exercises in the GitHub repository. Day 2 and day 1, people who couldn't run the day 1 exercises can do that, and also run the day 2 exercises, and then see you tomorrow. Okay, bye.
Bye.